Hello and welcome to an episode of The Central Equilibrium. I'm Eric Kai, the chemical statistician, and I'm pleased to welcome my guest, Mandy Gu, who will talk about word embeddings and text classification. Mandy, welcome to The Central Equilibrium.
Thank you, Eric.
Tell us about your educational background.
So I'm a recent graduate from the University of Waterloo. I studied mathematics there with a major in statistics.
Mm-hmm. Congratulations on finishing your bachelor's degree.
Thank you.
And tell us about your current occupation.
So I'm currently working as a computational linguist at kite.ai.
Okay, and that is a company in Waterloo?
Yep.
And you just got this job recently, so congratulations on that too.
Thank you.
And tell us your overall objective for today.
So my overall objective for today is to give an overview of natural language processing. So this is how computers, machines analyze human languages, and I'll do that with an example using text classification and word embeddings.
Okay. I met Mandy when I was attending the 2018 Canadian Statistics Student Conference, which was held at McGill University in Montreal earlier this year. I don't think we didn't meet personally at the time, but I just attended her presentation. I was very impressed. She built a chat bot based on her collaborators' Facebook messages, and that presentation won the Best Undergraduate Presentation Award at the 2018 Canadian Statistics Student Conference. So a third reason to congratulate you, Mandy. I'm so thankful that Mandy came all the way to Toronto to film The Central Equilibrium with me for this episode, and I'm very excited about this topic that we're going to talk about because I don't know much about natural language processing or text classification. I will say that this episode draws upon some concepts that we've already covered earlier in either the Central Equilibrium or in my video tutorials. So we're going to talk about Bayes' theorem. And Bayes' theorem was covered earlier by my guest Arnab Chakraborty in two episodes, first on Bayes' theorem and second on the Monty Hall Problem. So if you haven't watched those episodes yet, I encourage you to do that first. This episode will also focus on the naive Bayes classifier. And there is an earlier video tutorial in my YouTube channel about naive Bayes classifiers. So if you haven't watched that video yet, I encourage you to do that first. I should say finally that Mandy summarized her research project about the chatbot based on Facebook messages in a blog post on her Medium blog. And so I'm going to put the link to her Medium blog in the description of the video down below in the show notes, but here it is. It's medium.com/@MandyGu. So it's one of her recent blog posts about this chatbot that she built. So it's very interesting. I'm so excited that you're here. Okay, so let's begin. I don't know much about text mining or text classification or natural language processing, and when I think about text and think about how to manipulate them or work with them in mathematics, I'm not sure where to begin or how best to represent them using mathematics. So how are text objects represented mathematically?
So this is where word embeddings come in. So word embeddings is also a part of feature learning in natural language processing. So if we want to be able to model text, so if we want to be able to model language, what features do we extract from our phrases, our words, such that we can put it into our model? So with word embeddings, we're actually creating a vector to represent our phrases, our words, and we're mapping these words into a set of real numbers.
Okay. So in short, a word embedding is a mapping from the text that you're working with to some set of real numbers.
Correct.
Okay. And what is a common, easy to understand example of a word embedding?
So one of the easiest examples of a word embedding is known as bag of words, and is also known as the count vectorizer.
Okay.
So this is typically the method that they teach you in introductory courses at school. It has many practical applications, and it's one of its major advantages is just how simple it is to create these embeddings.
Okay, so shall we go through an example?
Yeah, sounds great.
Okay, so I'll erase the board, and this is going to be a little involved because we're going to write a set of words. Even though it's a short set of words, we're going to have to map the words in this text into a vector of some sort. So we're going to have to be very rigorous, very careful here. So this is, I'm going to write at the top. So this is a bag of words. Also known as a count vectorizer.
Yep.
Count vectorizer. Okay, so you're gonna write a sample set of words, and then we're gonna map them into a vector.
Right.
Okay.
So before I do that, I kind of just wanted to give a preface of this problem and where we might encounter it in real life.
Okay.
So the problem that I'll be going over today is classifying its text classification.
Okay.
Given a phrase, we want to be able to classify whether or not this phrase is toxic.
Uh-huh.
So there's a lot of real-world applications to this. For example, if you're a forum moderator and there's way too many text messages for you to look through as a person, you could perhaps build a classifier to make these early detections.
Okay. So when Mandy talks about a forum operator, what she's referring to is an online discussion forum, like perhaps Reddit or Stack Exchange. I don't know if Stack Exchange would be considered, but I think Reddit is a good example where civility or respect is often expected. And the moderator of that forum wants to make sure that the things that are being written on the forum have some minimum standard of civility and respect, but that moderator would not have enough time to go through every single possible message. And so it would be really nice if there was some algorithm to classify the messages as toxic or not.
Yeah, correct.
Okay.
So the first step before we can actually start building this algorithm is we need to be able to create word embeddings, specifically bag of words embeddings for our phrases.
Okay.
So like most models, the data we collect are data that we previously observed.
Okay.
So possibly here some manual work might be involved in labeling our previous data as whether they're toxic or not toxic.
Okay.
So let's consider for our simple example 5 phrases which have already been pre-labeled as toxic or not toxic.
Okay.
So we have our first phrase, which is "You are stupid and dumb." So this would be an example of a toxic phrase, things that we do not want the people on our forum to be talking about.
Okay.
So a second phrase is also a toxic phrase, and this is "shut up and get lost." So now this person also adds an exclamation mark at the end of their phrase.
Okay.
So, and then now we have a not toxic phrase, and this phrase is called "how are you doing?" So it's a greeting. And then our fourth phrase, which is also a not toxic phrase, is "please continue." And then finally, we wrap this up with our last phrase, which is also not a toxic phrase. "That sounds great." So to make it a little bit easier to see, I'm going to use the blue to show which phrases are toxic by putting a little T at the front.
Right. Okay.
So we have 2 toxic phrases and 3 non-toxic phrases. The first thing we want to do before we even get to the embedding stage is we want to pre-process our words.
Okay.
So typically in a chat forum, some people might not spell words properly, or they might use weird symbols, and we want to normalize all of these.
Okay.
So normalization in in natural language processing is the transformation of these words into a more consistent form.
Okay.
So common practices include removing symbols, making everything lowercase, and removing certain words.
Okay.
So one thing that you have to be really careful about when you're normalizing is that you don't want to throw away valuable information.
Okay.
For example, in some cases, the punctuation marks might be predictive of which class the phrase would fall into.
Right. Okay.
And usually the best way to find out which steps you should take in normalizing is by trying them out and then testing them on a smaller data set to see which one performs the best. So for simplicity, we can say that we ran a few experiments and we decided that punctuation has no effect on whether or not a phrase is toxic.
Okay.
We can also say that capitalization has no effect on whether or not a phrase is toxic.
Okay.
So since we made these decisions, what we want to do is first of all remove all the punctuations and turn all of the capital letters into lowercase letters.
Okay. So I'll erase the punctuation marks and take away the period. Okay.
So I can change the capital to the lowercase.
Okay.
So there's actually other ways. There's other ways of normalizing text as well. One very common method that we're not going to use today is called removing stop words.
Okay.
So stop words are a set of words from the language that some experts have determined do not add to the semantic value of the sentence.
Okay.
So these are words like and, because, are, that if we remove in theory, it wouldn't affect the predictions. Another thing that we could do to normalize words is to lemmatize or stem. So when we encounter words that are not in its root form, this could sometimes create some noise, and we want to show that something like sounds is exactly the same as the word sound or sounded.
Okay.
And then so lemmatizing and stemming reduces these words to their base form.
Okay.
And the difference between the two is that when you stem, you're stemming the word by itself, whereas the lemmatizer will consider the entire context to determine which particular usage of this word it is.
I see. Okay.
So these are more advanced techniques for normalization, and so for simplicity, we're not going to show them today.
Okay.
We're just going to remove the punctuations and lowercase all the words.
Okay. We're just going to change this to lowercase as well.
Nice catch.
Okay, thank you. Okay, so we're not going to do the stemming or the lemmatizing.
Yep.
Okay, but I think what she just mentioned there, those sound like very sensible things to do, and in a real world application, we may need to do those things. But for simplicity, we're just going to focus on how to map these into a vector.
Right.
Okay.
So last thing I want to talk about before we actually start with the embedding. So one thing you want to determine when you're creating these vectors is what granularity level do you want to do this.
Okay.
So typical choices are you want to do them at the word level. I want to create embeddings that reflect every word.
Okay.
But sometimes you may need to create embeddings which reflects every character, so every letter. Or possibly you want to do groups of words or groups of letters.
Okay. Can you give a simple example of where that difference becomes meaningful?
So from a linguistics point of view, we may have a longer word, but then they're made up of a prefix and a suffix, and these might hold different semantic values.
Okay.
So, but vectorizing on the word level is probably the most common approach, and this is also the approach we're going to take today for simplicity.
Okay, but just to be clear, sometimes we need to vectorize on. We need to vectorize those prefixes or suffixes. I'm sorry if I'm getting the plural forms of those words wrong. I should know those. But you're saying sometimes we need to go even more granular than just the word.
Yeah, and then sometimes we also create character level embeddings.
What's a character level embedding?
So T would be its own vector, H would be its own vector, like that.
Okay. When would a character level embedding become important or valuable?
So usually when we're doing a very complicated NLP task, sometimes we'll want to concatenate embeddings. So possibly we can do word level embeddings concatenated with letter embeddings, with character level embeddings. And the rationale behind that is that the combination, the sequencing of certain characters means certain things.
Okay. All right, so all really interesting stuff that we're not going to get to today, but I really appreciate Mandy bringing these things forward for us to know and consider. Okay, so now can we? Okay, so now we can vectorize, right?
So now we can vectorize.
Okay, all right. Let's vectorize.
So I'm gonna erase this, so I'm gonna erase this, and I'm gonna.
I'll erase. I'll erase. Okay. Okay, go ahead.
So hopefully you still remember or have some sort of recollection of what those words are.
You can, audiences at home, you can always rewind the video and go back to what the phrases are. Because of a lack of space, we just have to erase and now write the vectors. But go ahead, please.
So one thing that I probably should have put up while the phrases were there is that one important thing we want to know is how many words are in toxic, how many words are in toxic phrases in total,
okay,
and how many words are in non-toxic phrases in total.
Okay.
So let's just keep track of this here. So
sure.
Number of toxic words. So in the example we just gave, this happens to be 10. And then we have the number of not toxic words, and there are 9 of these. So in total, we saw 19 different words.
Okay.
So now we want to create a comprehensive vocabulary.
Okay.
So the difference between the vocabulary and the words is that the vocabulary is the unique set of words.
Okay. So, so a word can appear multiple times in your what's the noun that I should be using?
I mean, you can call them a phrase, or you can call them or you can call them a document, but we should just call them phrases for simplicity.
Okay. So there could your phrase can have many words, but some of them may repeat.
Right.
And so the vocabulary is the number of unique words in your phrase.
Yeah.
Okay.
So I'll just write down our particular vocabulary. So our vocabulary, we have you, and then we have are, we have stupid, and dumb. So this is all from the first phrase, if you recall.
Uh-huh.
We also have shut up, get. So you notice it was shut up and get lost, but we're omitting the and because they're already appeared. So
right.
Get lost.
Okay.
So I'm not going to write all of them out because it's quite a long list, but then you get the idea. This is our vocabulary.
Right.
So to create these bag of words vectors, what we're doing is we're considering our phrases, phrase 1 through phrase 5.
Mm-hmm.
And we are creating a matrix.
Uh-huh.
Where this is so let V1 be the first word in our vocabulary, and this is you.
Okay.
We have V2 be the second word in our vocabulary, which is are.
Uh-huh.
All the way till the end of our vocabulary.
Okay.
And the element in the matrix is how many times this vocabulary word appears in this particular phrase.
Okay. You know what? I think vocabulary is such an important term here. I'm just going to make sure we write down the definition here. So vocabulary is the set of unique words in our phrases. Right? It's the set of unique words in our phrases. Okay.
So our phrase 1 was you are stupid and dumb.
Uh-huh.
So here we see there's one occurrence of the word you, one occurrence of the word are,
uh-huh,
and so forth. And then we saw our phrase 5, the non-toxic phrase, which was that sounds great.
uh-huh.
So that sounds great does not contain you and it does not contain are, so we put a 0 here. So once we have this matrix, this becomes so we call these the embeddings. Specifically, the count vector or the bag of words representation for phrase 1 is shown here.
Uh-huh.
And then for phrase 5, it's shown here. So our vectors goes this way.
Uh-huh. Okay. So just for everybody at home, in case I think Mandy made it very clear earlier verbally, but just just to make this in writing, V1 is the word you, and V2 is the word are. And so 1 is the number of times you appears in phrase 1, and 0 here is the number of times that the word you appears in phrase 5. Okay.
So now that we have these vector representations of the phrase, we can feed them into pretty much any classifier to start making the distinctions between the toxic class and the non-toxic class.
Right. So now that we have a mapping from the words into some matrix containing real numbers, and now we can feed this into whatever statistical or machine learning algorithm we want. Mm-hmm. Okay. Cool. Okay. So this is a nice simple example of a word embedding in the form of a count vectorizer. We have mapped the text into a matrix of real numbers. What is a common technique that we can use to classify a phrase into whether it's toxic or non-toxic? So this is a binary classification, right? So what is a common binary classifier that we can use in natural language processing?
So right now, the state-of-the-art classifier is probably a neural network, but a more simpler classifier that is still used would be a naive Bayes classifier.
Okay. So as I mentioned at the beginning of the episode, I have an earlier video tutorial on the naive Bayes classifier. If you haven't watched that video yet, I encourage you to do that first. Okay, so please, Mandy, continue.
Okay, so now that we have our vectors, we can actually move to the classification.
Okay.
So probably.
Yes. Let's erase everything. So we're gonna move on to the classification here.
So when we encounter a new phrase, something we've never seen before, we want to be able to make the prediction whether or not it's toxic. So say that a user on our forum says, "Get away." And we want to see, okay, is this a toxic phrase or is this not a toxic phrase?
Right.
So recall Bayes' rule, which is that the event of A occurring conditioned on B is equal to the probability of B conditioned on A multiplied by the probability of A occurring over the probability of B. So this is Bayes' rule.
Right. Or Bayes' theorem. Mm-hmm. Yeah.
So Bayes' theorem. And from a natural language point of view, we can do something very similar.
Okay.
So ultimately, what we are interested in is the probability of the phrase we encountered being toxic. So given the phrase "get away," so given the phrase "get away," we want to see what's the probability that it's toxic. And we want to compare this against the probability that "get away" is not toxic. So if the first probability is larger, then I think it's fair that we can classify "get away" as a toxic phrase.
Yes.
Otherwise, we classify "get away" as a not toxic phrase.
That's very sensible. Right.
So
and I think it's sorry to interrupt. I think it's important to emphasize here. This is a new phrase. If we can look at the 5 phrases that we had in the beginning, the phrase "get away" did not appear in those five phrases. So this is a new problem for our classifier to figure out. Mm-hmm. Okay.
And one other thing that I wanted to make a point of, so the word "get" actually appeared in one of our phrases.
Yes.
Shut up and get lost.
Yes.
But "away" did not appear in any of our phrases. So "away" is a new word in our vocabulary.
Okay.
So let's first calculate the first one, and then we'll calculate the second probability.
Okay.
So the conditional independence clause of Bayes tells us that calculating something. Okay, actually, sorry. Let's just take a step back. We need to apply Bayes' theorem first.
And we should say the conditional independence clause is in the naive Bayes classifier.
Right.
Yes, okay.
So first let's apply Bayes' theorem. So we have this event and then this event.
Yes.
This is equivalent to the event of, we know a phrase is toxic, and this phrase and then given that we know a phrase is toxic, the phrase happens to be get away. And then we have the probability of, any phrase being toxic divided by the probability of observing this phrase get away. So let's start by examining the probability of a phrase being toxic. So this is so there's many ways we can use to approximate for this probability.
Or estimate this probability given our training set.
Right. So everything we know so far is given on our training set, which is the 5 phrases we saw. We cannot assume any additional knowledge, any other data that we may have seen, because that is our entire knowledge base.
Right.
So there's many ways we can use to find this, and typically a common way is to see how many phrases are there in total, and out of our total number of phrases, how many are toxic.
Okay. So we had 5 phrases.
Correct.
And we said that 2 of them were toxic.
Correct.
So then we're going to estimate this probability by the proportion of toxic phrases, which is 2 out of 5.
Right. So
okay.
So this here is 2 out of 5.
Okay.
So another thing that I kind of wanted to draw your attention to. Sorry.
Just going to make that nice and big for everybody else to see. 2 out of 5. Yep.
So another thing I wanted to draw your attention to is the denominator. So the denominator here is the probability of observing the phrase get away. Now this would not be very easy to calculate for, but fortunately we had noticed that even if we're looking at the probability of seeing get away and it being not toxic, that the denominators are the same.
Yes.
So what this means is that what this means, I'll just
erase whatever you need. Erase whatever you need.
So what this means is that if we want to compare, so if we wanted to compare these two, which is essentially what we wanted to do for this classification problem. So the comparison of these two is equivalent to comparing the probability of observing get away given that the phrase is toxic multiplied by the probability of toxic. So comparing this product against observing this phrase given that the phrase is not toxic multiplied by the probability that it's not toxic.
Right. If I could try to just, I know I'm going to be very tedious here and being redundant, but just to make it crystal clear to everybody at home. So this was the.
Sorry, just the A.
Oh, sorry. Thank you. Get away. This is what Mandy wrote before. This is how to use Bayes' theorem to get this conditional probability. If we write the same thing for P of not toxic condition on this phrase get away, we will notice that we will notice that the two denominators are the same, right? And our goal is to determine which of these two probabilities is higher. Well, if these two denominators are the same, then we don't need to worry about comparing these denominators. We can just worry about comparing the numerators. And as Mandy said, not only is this unnecessary, this is also often difficult to estimate or difficult to calculate. So getting rid of this is a really good simplification, and we can just focus on the numerators.
Right.
Okay.
So yeah, thank you for the explanation, like the additional explanation.
Yeah. I'm sorry for being redundant, but I think it's good to make that crystal clear so that everybody understands why we're getting rid of a probability. Okay, sorry. Okay. Continue, please.
So now that we know, all we need to do is compare these two. So this probability, as we shown earlier, is very easy to estimate for.
Yes.
So initially we said that the probability of observing a toxic phrase by taking its proportion is 2 out of 5. And similarly, by taking its proportion, the probability of observing a not toxic phrase is 3 over 5.
Right.
So this leaves the question of how do we calculate this component? So the calculation of this component is going to be a little bit more difficult, so we're going to do this on its own, and then afterwards sub it back into this equation and compare which one is greater.
Right.
So let's start by calculating the probability of observing the phrase get away when we know the phrase is toxic. So by the conditional independence clause of naive Bayes classifier, this is equal to, so this is equivalent to, where we actually see get away as the union of the word get and, the intersection of the word get and away.
Intersection, yes.
And then this would give us the probability of get given toxic. So I'm going to put this in double quotation so we know that it's a word multiplied by the probability of away given that it's toxic.
Right. And so this is, we're multiplying these two probabilities together. And just to be clear, when Mandy said earlier, this is an intersection, so we're saying that it's the probability of get as a word and away as a word, the intersection of these two events together, condition on the phrase being toxic. Okay, so the conditional independence assumption, so this is, we're assuming, I think it's good to say that this is an assumption here. We're assuming here that this event could be broken down into these two events multiplied together. Right.
So oftentimes this, in real life, this does become a very dangerous assumption. And this is part of the reason why naive Bayes earns the name naive.
Right. Yes. Very good. Okay. So now that we've made this conditional independence assumption, the calculation of these individual probabilities is a lot easier now, right?
Right. Yeah.
Okay.
So, but one
I shouldn't say a lot easier, but as we will see, it's actually not quite as easy. And so Mandy's going to explain why. Yes.
So one thing that you might notice right now is, so as we pointed out earlier, get is in the vocabulary from shut up and get lost. But away is not present in any of the 5 phrases that we've encountered. So the problem with taking the product of these two probabilities is that this probability, the probability of encountering away when you know the phrase is toxic, is theoretically 0, because from all of our prior knowledge we saw that we never saw the word of away. We do not know if it can exist or not.
Right.
So this makes it really hard to do inference with naive Bayes classifier when a word's not in our vocabulary.
Right, because if this probability is 0, then 0 times this probability is 0. And if the probability is 0, then that's not going to be useful for us for the classification. Remember, we're going to have to calculate this same probability for not toxic as well. And if both probabilities are 0, then we can't compare them, right? Aside from the fact that a 0 probability by itself is not realistic, not helpful, right? Okay.
So what we do instead to counteract against this is, so this is what smoothing is for. So by using a smoothing parameter, we're able to approximate for a very low probability of this occurring, and as a result, this entire probability will not be 0.
So Mandy, could you define for us what smoothing means in this context?
So smoothing, we add a smoothing parameter, and this is often denoted as alpha. And this alpha ensures that, so we add an alpha to the numerator, and this ensures that this entire probability never becomes 0. However, we must take an extra step to ensure that this probability never exceeds 1. And as a result, we also add something to the denominator. Let's erase the board, and then we can talk more about the smoothing. So.
And should we emphasize this particular type of smoothing is called Laplace smoothing?
Right. This is called this particular smoothing is called Laplace, and we're actually going to be doing.
I'm going to write Laplace smoothing on the top. Okay, so Laplace smoothing.
So.
Okay.
We're actually going to be using a special case of Laplace smoothing. And this is the special case where alpha equals to 1.
Okay.
So as we were talking about earlier, you never really know what works for a particular data set. We don't know if for our particular data set, alpha equals to 1 would be the best smoothing parameter. So if, say, we were trying to build this toxicity classifier in real life, ideally we'd want to try out like at least a few alphas and then pick the one that works best with our data set. But I think that from a simplicity approach, choosing alpha equals to 1 is a fair place to start.
Okay. And I think what Mandy just talked about here is a very common practice in machine learning and predictive modeling. Your predictive model contains a certain parameter that is chosen arbitrarily. It's a tuning parameter. Think about lasso regression, for example. There's a tuning parameter, and there's that penalty parameter in lasso regression, and you're going to have to figure out what value of that parameter should be, and there's no good theory or hard and fast rule about what that should be. So the best that you can do is just try a number of different values, and come up with some metric to determine which of those values is the best. So come up with some criterion for the predictive accuracy. And then based on the model or the parameter with the best predictive accuracy, choose that value. So what Mandy just talked about is we need to try a number of different values for alpha before we settle on the one that works best.
Right.
Okay.
So actually, there's a theorem called for this in machine learning, and it's called the no free lunch theorem, which is exactly what Eric just described.
Right. I wrote a short blog post about the no free lunch theorem on my blog, The Chemical Statistician. So if you haven't read that blog post yet, please feel free to visit my blog. Okay, all right, let's continue.
Okay, so let's first consider a scenario where we decide not to smooth.
Okay.
So why would we ever consider this? Well, for example, if we believe that our vocabulary is comprehensive enough that we would never encounter a new word, or perhaps we want to treat unfamiliar words a little bit differently, then possibly we can consider this. But definitely the standard would be to introduce a smoothing parameter.
Okay, so no smoothing, right?
Sorry, no smoothing.
In this case, the suffix is important. Okay. Yes. Okay.
Okay. So in our example of get, so we can do this with get because get is already in our vocabulary. What we do is we're really just looking for proportions. First, we're going to, in the numerator, we're going to find how many times get appears in a toxic phrase. And I believe we found 1.
Yes.
And then we want to consider all the words found in toxic phrases, which we actually said this earlier was 10.
Yes.
So the probability of observing get when we know that the phrase is toxic is 1 over 10.
Right.
So so this is with no smoothing.
Right.
But this is for our intents and purposes, because our vocabulary is so small, this is not what we're going to use.
Okay.
So I'm just going to erase this, and then we're going to go to what happens when we smooth.
Okay.
So given an arbitrary word and given an arbitrary class, so the word here can be get, it could be away, it could be a complete new word like fruit or something else. And then, of course, for our problem, our classes is toxic or not toxic. The probability of this with smoothing is the number of times this word appears in this class. Number of times, I'm just gonna be a little bit more concise to be space efficient. So
no worries.
Number of, let's just say appearances, and then number of appearances, number of word appearances, so this particular word in our particular class. And here we add the smoothing parameter, which we decided to be 1. So I'm just gonna write here that we chose this to be 1. And in the denominator,
so this is, just to be clear, this is the number 1 right here.
Right.
Yeah. Okay.
Thanks for that.
No worries.
So in the denominator, we want to say number of words in this particular class, and to prevent this probability from ever exceeding 1, because this could possibly be 0, we also add the total number of words across all classes. So total number of words, so in our particular example, the total number of words is 19.
Yes.
Because we have 10 from the toxic phrases, 9 from the non-toxic phrases.
Yes.
So just a clarification, these total number of words is not the vocabulary. We're not taking the unique number of words. We're taking the total number. So if one word, so as we saw, the word and got repeated a few times, we're double counting for all the times that it appears.
We're counting we're counting the number of times that and appears in total, regardless of whether it appeared uniquely or it appeared repeatedly. Okay.
So this is the new calculation that we want to work with.
Right.
So before, we first wanted to calculate observing get given the toxic class. So this is equal to the number of times the word get appeared in the toxic class was 1 from shut up and get lost.
Right.
And then we have our alpha, which is 1. We're dividing the total number of words in the toxic class. And
which was 10.
10,
right?
Yes. And then the total number of words
is 19.
Right. So this is equal to 2 over 28.
29.
Sorry, 29. Good catch.
No worries, no worries.
So this is equal to 2 over 29.
Okay.
Now we have the probability of observing the word away given that it's toxic. So now away does not appear anywhere in our phrases.
Right.
So the number of times the word away appears in class toxic is 0. We add our smoothing parameter of 1. And our numerator is the same, the number of words appearing in toxic class, which is 10, plus the total number of words, which is 19. So this here is equal to 1 over 29.
Okay, cool.
So let's write this at the top, because this would be pretty important for later.
Yes.
And we kind of want to be reminded of what our numbers are.
Okay.
So we have P get given toxic. So this is equal to 2 over 29. And then we have P of away given toxic is equal to 1 over 29.
Okay, so now we need to calculate P of get condition on the phrase being not toxic,
right,
and P of away condition on the phrase being not toxic.
So the next, so let's start with P of get given not toxic.
Okay.
So
let me try to do this one. Okay.
Sure.
So the word get appears. So yeah. Let me take a look at
the phrases.
The phrases. Yeah, and everybody back home, if you need to go back, rewind the video to look at the phrases. So the word get does not appear in the three non-toxic phrases. So
Correct.
it should be 0 plus the smoothing parameter alpha, which is 1. We're going to divide by the number of non-toxic words, which is 10.
Non-toxic.
Oh, I'm sorry,
9.
9. Thank you. 1, 2, 3, 4, 5, 6, 7, 8, 9. Thank you. And the total number of words is 19. Yes.
Yes.
19. Okay. So this is equal to 1 over 28.
Okay. So do you want to calculate the next one as well?
Yes. Let's calculate the next one. Okay. So P of away conditioned on the phrase being not toxic is equal to, so it's obviously 0 because the word away does not appear in any of our phrases, right? Plus 1, which is the smoothing parameter, divided by the number of non-toxic words, which is 9, plus the number of words in total, counting duplicates,
So
which is
19.
So this is again 1 over 28.
Right.
Okay.
So I'm just going to summarize this like that.
Okay.
But great job, Eric.
Okay. Thank you.
So Eric, as Eric found, the probability of get, given that it's not toxic, is equal to 1 over 28. And
Yes.
similarly, the word away, which does not appear at all, so observing this word condition on the phrase being not toxic is also 1 over 28. So previously we found that get away is the intersection between get and away. And using the conditional independence clause, the probability of get away over toxic
Condition on toxic.
condition over on toxic is equal to the product of P get condition on toxic multiplied by probability of away condition on toxic.
So this would be 2 over 29 times 1 over 29.
Yes.
Okay.
So this is around 0.002.
Okay. So now we need to do the same thing for not toxic.
Right. So the probability of observing the same phrase conditioned on it not being toxic is we take get this component, which is 1 over 28, and then the probability of way condition on not toxic is also 1 over 28, so it would be 1 over 28 squared.
And this is equal to?
This is around 0.001.
0.001. Okay.
But we can't make the comparison just yet, because if we remembered, there were 2 components in the numerator.
Yes, that's right. So we need to multiply this by the P of not toxic and this by the P of not toxic.
Right.
Okay.
So sorry, we multiplied this by the probability of toxic and this one by the probability of not toxic.
Yes. Okay, yes. In case I said that incorrectly, I'm sorry about that. Yes. So yes.
So we have the probability of get away given that it's toxic multiplied by the probability of toxic. So this is around.
So this is 0.002. This is 0.002 times, is it 2 over 5?
It was 2 over 5.
Okay, and this is roughly equal to?
So this is. Oh shit! We didn't calculate these ahead of time.
Oh, okay.
So.
That's okay. That's okay.
So why don't I write out the next line and
Okay.
then you can find the calculation.
Okay, sure. Yeah. Good idea. Okay.
So the other number we're interested in is the probability of observing the phrase get away given that it's not toxic times the probability that it's not toxic. So this is around, we saw here that the probability of get away conditioned on it not being toxic is 0.001 and this we said was 3 over 5.
Right.
So this is...
It's okay. I got this. So this is equal to 0.0006. Right. So for everybody at home, the 2 over 5 comes from the fact that there were 2 toxic phrases out of 5 phrases in total. So it's 2 over 5 here. And this is 3 over 5 because there were 3 phrases that were not toxic out of 5 phrases in total. Yeah.
So these two numbers, sorry. So this number and this number are what we are concerned about.
Right.
So the probability of the probability of observing this getaway phrase, given that it's toxic times the probability of toxic, is 0.0008, which is slightly bigger than 0.006, the probability of getaway, given that it's not toxic, times the probability of not toxic.
Right.
So earlier, as we said earlier, we don't care about the denominator because the denominator of these two are the same. So in this case, we would go with a larger probability. So the slightly larger probability is that this phrase get away is considered to be toxic.
Okay, so that's how the naive Bayes classifier is applied for this particular new phrase. We calculate the conditional probabilities and we use the conditional independence assumption to make the calculation simple for us. And we found that this probability is higher than this probability, and so we conclude that this phrase is toxic. And from a human intuitive, in terms of human intuition, I do think that the word get away is rather toxic. So this classifier worked.
Yeah.
I think so. Okay. All right. So why don't we try another example here? So you've shown how to do this. I want to try and apply what I know. So why don't you give me a phrase, Mandy, and I'll set up the calculation. At least I'll set up the calculation.
Okay, that sounds good. So we're going to use the 5 phrases from before as the 5 phrases that we know. And this new phrase is going to be that sounds very good.
That sounds very good.
If you recall, no punctuation, we normalized this ahead of time.
Yes.
So if you recall, that sounds good was one of our phrases, but the word very actually never appears. So with this, we would have to use a smoothing parameter as well.
Okay. So our task is to calculate the probability given this phrase that sounds very good. Given this phrase, what is the probability that this phrase is toxic? And same thing, given this phrase, what is the probability that this phrase is not toxic? Okay, so let's do the one at the top. Let's do this one first. So by Bayes' theorem, this is equal to P of that sounds very good, conditioned on the phrase being toxic, multiplied by the probability that the phrase is toxic, and divided by P of that sounds very good. But as we mentioned earlier, the denominator we do not care about, and so we can just ignore this. And instead of writing the equal sign, we'll say that it is just proportional to this. And this, calculating this, is all that we care about.
Right.
Okay, now, by the assumption of conditional independence, we're going to simplify this probability right here to, so assume, okay, this is going to be equal to P of that conditioned on toxic times P of sounds conditioned on toxic times, here, let's put the multiplication sign down here, times P of very conditioned on toxic times P of good conditioned on toxic times P of toxic. Okay, so now we need to go back to our phrases, look for the words that sounds very and good in the toxic phrase in the two toxic phrases, and calculate the proportions in which they appear in the toxic phrases to estimate these probabilities. And we're going to use Laplace smoothing to do that for us.
So we can still keep with the alpha equals 1.
Yes, we're going to use alpha is equal to 1. Okay, so Mandy, I'm going to ask you to write down the formula. I'm going to ask you to help me to plug in the numbers because I don't have them in front of me. So first, it's P of that condition on toxic.
Yep.
And so this is the number of times the word that appears in the two toxic phrases. So
yes.
So number of appearances of that in toxic phrases plus the alpha smoothing parameter divided by number of words in toxic phrases plus number of words in all phrases.
Right.
Okay. Duplicates included. Remember, these two numbers include duplicates. Okay. So Mandy, how many times did the word that appear in the toxic phrases?
So it did not appear at all in the toxic phrases.
It did not appear. So it will be 0 plus an alpha of 1. And I think we had 10 toxic words plus 19 in all phrases, right?
Yes.
So this is equal to 1 over 29.
Mm-hmm.
Okay. So analogously, so we have that sounds very good. So sounds condition on toxic. The calculation would be how many times is the word sounds?
It does not appear in the toxic class.
Does not appear. Okay, so 0 plus 1 divided by 29. That's equal to 1 over 29. Okay, let's do P. Now, very, that's the interesting. That's the new word.
So very does not appear in any of the phrases.
So we're going to have to go with 0 plus 1 divided by 29, which is 1 over 29.
Yep.
Right? And then lastly, I'm going to have to erase something here. Okay, so what am I going to erase? Okay. You know what we'll do here is we'll record the numbers at the top, just like Mandy did in her example. So this we calculated as 1 over 29, and so okay. So we have these two here. So now P of that sounds good. Condition on toxic.
So good also does not appear in any of our true toxic phrases.
Okay, so it's 0 plus 1 over 29, and that's equal to 1 over 29.
Correct.
Okay, so now we need to multiply these four things and then multiply that by P of toxic, right? Okay, so yeah. Okay. So P of that given toxic times P of sounds given toxic times P of very given toxic times P of good given toxic times P of toxic. This is equal to 1 over 29 to the power of 4 times, and we said that there were 2 toxic phrases out of 5 toxic phrases in total.
Yeah.
Okay.
So we actually don't have to calculate this number. We can leave it here.
Yeah, okay.
Later it will become very apparent which probability is greater.
Okay. So we're not going to go through every little detail for the not toxic calculations. What we're just going to do is write down what we need to calculate, and then we'll write down what the number is at the end. So we need to calculate P of that given not toxic times P of sounds given not toxic times P of very given not toxic times P of good given not toxic times P of not toxic. Okay.
So we're just calculating this right away, right?
Yes. So I think it would be a good exercise for everybody at home to mirror what we just did for the toxic phrases and do the same thing for the not toxic phrases. So we're just going to show the end result at the end, and you can compare. Okay. So Mandy, what do we have for? Let's start with these 4 probabilities. What do we have?
Okay. So that sounds good already appears, and all of them appears exactly once in a non-toxic phrase.
Okay.
So the probability of that, seeing that given not toxic, would be 2 over 28.
Ah, right.
And it's 28, which is different from this 29 because the denominator, there's
right.
in total 9 not toxic words and 19 total words, which gives us 28.
Right. So this is equal to, so it's for this it would be 2 over 28?
Yes.
Because it's 1 for one appearance of that plus 1 for the alpha smoothing parameter. Right. Okay. So 1 over 28 times 1 over 28.
Oh, sorry. 2 over.
Oh, I'm sorry. Thank you. I just said 2 over 28. 2 over 28 times 2 over 28 times 1 over 28.
Yeah, because the word very does not appear
in any. Times 1 over 28 times 2 over 28, and we have 3 non-toxic phrases out of 5 out of 5 phrases in total. So that's 3 over 5.
Correct.
Okay. So we are comparing. So this is equal to. So this is equal to 2 times 2 is 4 times 2 is 8 So this is 8 over, okay. So okay, you know what we'll do? We'll just say that this is equal to, okay, so this is equal to 8 over 28 to the power of 4?
Yes.
Right? Times 3 over 5.
Mm-hmm.
Okay, so I don't think that we need to do we don't actually need to calculate these to figure out which of these two is bigger, because the numerator is bigger for this, right? The denominator on so this is going to just reduce to 29 to the power 4, right? Okay, so the numerator is bigger here. The denominator is smaller here, so this overall fraction is going to be bigger, and you're also multiplying by a bigger fraction here. So it is obvious to us, without actually doing the calculation, that this probability down below is bigger than this set of calculation down below is bigger than this set of calculation up here. And so the conclusion is the phrase "that sounds very good" is not toxic.
Yeah.
Okay.
So that makes a lot of sense too, because this phrase to us, like, we can clearly identify it as not being a toxic phrase.
Right.
And this is very well reflected by our classifier.
Right. Okay. So I'll just write that. Yeah. We'll just write the conclusion very quickly. Very quickly. So the conclusion, just like Mandy wrote, conclusion that sounds very good is not toxic. Okay, and as Mandy just noted, based on just human intuition, I think that this makes sense. Excellent. Okay, so we have just used the naive Bayes classifier to classify two new phrases as toxic or non-toxic based on the very small set of 5 phrases, and was it 19 words in total?
19 words
19
in total.
19 words in total. So that is our training set. And we also use Laplace smoothing to help us, because some of the words in these two new phrases did not appear in our training set. Okay. Okay. So this was very educational for me. I know it sounds like I knew I was doing it at some point, but really, Mandy did a really good job of explaining all of this to us, from word embeddings to count vectorizers, to naive Bayes classification, and to Laplace smoothing, and combining all of those things, we made 2 pretty good predictions. Mandy, do you have anything more to add to what we've talked about today?
So, naive Bayes classifier, it's one of the more prominent uses of this classifier in natural language processing is actually as a spam detector. So identifying whether a text message, an email is considered spam or not spam. So this is where it kind of found its roots in NLP, and it's still, like, it's not as effective, it's not as powerful as something like a neural network, but it is a very simplistic approach, and what many people really like about it is the interpretability is very clear. Yes.
Well said. Okay. So whether it's our personal email accounts or our professional email accounts, spam detection is very important. And so now I know I have naive Bayes classifiers to thank for not getting all of those spam messages in my email accounts. Okay. This has been great. This has been wonderful. So, Mandy, a question that I like to ask for all of my guests is there a book or a website or a blog or an essay or something that you've encountered recently that something in math, science, or economics that you really enjoy and found to be informative?
So there is a book that I've been reading for the past year or so, and it's called Pattern Recognition and Machine Learning, and the author is Christopher Bishop. So this is a very comprehensive machine learning book. It goes over statistical machine learning methods such as expectation maximization, and also some of the more generic machine learning algorithms such as neural networks and support vector machines. So it's a very informative book, very comprehensive.
Okay. And I'll make sure to put the title of that book and the name of the author in the show notes in the description of the video down below. Okay. And finally, Mandy, how can people find you on the internet?
So as Eric mentioned earlier, I do have a blog on Medium, and my handle is just my name, Mandy Gu.
Okay, and I hand wrote the URL to her blog at the beginning of this episode, and I'll also put the URL down below in the description of this video. Okay, as always, okay. All right, so as always, my name is Eric Kai. I am the chemical statistician. If you'd like to learn more about statistics or chemistry or career development, you can visit my blog, The Chemical Statistician. You can watch my video tutorials on statistics or chemistry on my YouTube channel. You can watch more episodes of The Central Equilibrium, and I'll put the link to the channel page for The Central Equilibrium in the description of the video down below. If you have comments or feedback about The Central Equilibrium, please share them in the comments below each video. And of course, you can also follow me on Twitter at ChemStatEric. Thank you for watching this video, and I hope that you learned something useful today. And I'm sorry for the minor blackout that we had at the end of this episode. Thank you so much.